us to an example of the precipitation. Will a precipitate for when 250 ml, forget CaF2 for example. Suppose the question, will a precipitate form without determining the nature of this precipitate? When 250 milliliter of CaNO3 solution is mixed with NaF solution. So I have two beakers. The first is CaNO3 The second is NaF. So I have Ca2 plus and NO3 minus. In the second beaker, I have Na plus and F minus. So what are the possibilities? First, Ca2 plus might react with F minus, positive and negative, while NO3 minus might react with Na plus. So Ca2 plus F minus will give CaF2. Do we have a KSP value? Yes. So this is CaF2 solid. This is a possible reaction. The second is Na plus NO3 minus. That will give NaNO3. We don't have KSP of NaNO3. So NaNO3 is a strong electrolyte that will redissociate to Na plus NO3 minus. So we have a reaction, Ca2 plus F minus. We have a reaction, Na plus NO3 minus. We don't have a reaction. So we determine our reaction. This is step one. Step two is to calculate the concentration of all ions in the solution. And especially, it's not necessary to calculate the concentrations of the spectator ions. So we'll calculate the concentration of the ions involved in the precipitation. Ca2 plus initial. What is the meaning of initial? Ca2 plus at T equals 0 after dilution equal the initial concentration. What is the initial concentration? This is, don't forget that CaNO3 2 will give Ca2 plus 2 NO3 minus. So if we have 10 minus 4 molar, we obtain 10 minus 4 molar 2 times 10 minus 4 molar. So Ca2 plus initial is 10 initial in the beaker, 10 minus 4 times V initial times V initial. The V initial is, so we have 10 minus 4 times 250 ml divided by V total, which is 250 ml plus 750. Give me the answer, please. And, okay, I have to calculate. And we have NO3 minus. It's not necessary to calculate NO3 minus nor Na plus since they are spectator. We calculated F minus. F minus equal 10 minus 3 times 750 divided by 250 plus 700. So I calculated the initial concentration. Now I have to calculate IP. I write CaF2. Pay attention. Give Ca2 plus 2F minus. So IP equal Ca2 plus initial to the power 1 times F minus initial to the power 2. Okay? So we calculated IP. Therefore, now compare IP and KSP. If IP greater than KSP. So we will have a precipitation of CAF2. If IP equal KSP, so we are at the beginning or at the starting of precipitation, and if IP is less than KSP, we don't have precipitation. So we calculated IP, we observed that IP is less than KSP. IP is less than KSP, so no precipitate is formed. This is an example about the possibility of formation of precipitate when you mix two ions, one positive and one negative. We pass to another part, which is very important. The fractional precipitation. Suppose we have a beaker. What is the objective of this part? We have a beaker containing cation M plus and cation N plus. And we want to separate one of these ions. So what to do? We add M plus, we add L minus, that will form Ml solid, and N plus L minus, no reaction. What is the meaning? Addition of substance containing L minus will precipitate by theory M plus to Ml, but N plus did not form a precipitate with L minus, so N plus will be free in the solution. So what is the final result? M plus totally pass to the precipitate Ml, N plus remains in the solution. By simple filtration, we can separate Ml from the solution. So what is the objective, or what is the result? We separate M plus from N plus. So this is what we call the separation of ions. Can we separate totally M plus from N plus? Yes. If you add amount of L minus that precipitate completely M plus, so you can remove all M plus from your solution. But suppose you add a certain amount. Suppose you add L minus as limiting reagent. So in this case, L minus will remove a part of M plus. So we have M plus remained in solution, and in this case, we have fractional precipitation. We have a part of M plus that has been precipitated. Okay, so as a conclusion, what to do to separate two ions present in the solution? To separate two ions present in the solution, think about adding a substance that form a precipitate with one of the ions. According to the amount of L minus added, you can enter all M plus in the solution to the precipitate Ml. In this case, Ml will precipitate and N plus will remain in the solution free. By simple filtration, you separate Ml from your solution, so you obtain a final solution containing N plus. Another important point, the amount of L minus affect the percent of M plus that will enter to the precipitate. For this reason, we can add L minus to precipitate, for example, 50% of M plus. So in the final solution, after filtration, we will have N plus 100% is free, M plus 50% are transferred to Ml and separated, so we have M plus 50% of the initial M plus. So two ions can be precipitated out separately if they form salts of different solubilities with the same counter ion. Case 1, L minus precipitate M plus without precipitating N plus. So M plus can be separated from N plus. Suppose the second case that the two ions M plus and N plus react with L minus. So what to do? Consider the separation of silver and lead. I will pass to the sketchboard to explain. I have a beaker containing Ag plus and Ag plus and Pb2 plus, and I will add Cl minus given Ksp of PbCl2 equal 1.6 times 10 minus 5 and Ksp of AgCl, that is equal to 1.8 10 minus 10. So question 1, what would happen when Cl minus was added? By theory, Ag plus will react with Cl minus to give AgCl solid and also Pb2 plus 2Cl minus will give PbCl2 solid. So Ag plus and Pb2 plus can react with Cl minus. Okay. We know that. So by theory, we have formation of two precipitate. This is by theory. But we know that experimentally, the formation of precipitate depends on initial concentration of Ag plus, initial concentration of Cl minus, and the initial concentration of Pb2 plus. We said if Ip is greater than Ksp, so we have formation of precipitate. If Ip is less than Ksp, we don't have formation of precipitate. If Ip is equal Ksp, we have formation. We are at the starting of the precipitation. So this is the observation 2. 3. What is the real state of the solution? Pay attention. To form AgCl precipitate, Ip of AgCl should be greater than Ksp of AgCl. That means Ag plus in the solution initial times Cl minus initial in the solution should be greater than 1.8 times 10 minus 10. Suppose Ag plus initial in the solution is given equal 0.1 molar. Implies the Cl minus initial equal should be greater than 1.8 times 10 minus 10 divided by 0.1. So 1.8 10 minus 9. In other words, if the concentration of Cl minus in solution should be greater than 1.8 10 minus 9 in order to precipitate Ag plus. Okay, this is the concentration, the theoretical concentration of Cl minus that should be used in order to precipitate Ag plus present in the solution, and Ag plus present in the solution is given 0.1 molar. By the same way, we calculated what should be the concentration of Cl minus in the solution in order to precipitate Pb2 plus. So now calculate Cl minus initial to precipitate Pb2 plus. To precipitate Pb2 plus, Ip of Pb Cl2 should be greater than Ksp of Pb Cl2. Okay. So Pb2 plus initial times Cl minus square initial should be greater than 1.6 10 minus 5. So Cl minus initial square should be greater than 1.6 10 minus 5. Suppose the concentration of Pb2 plus initial is also 0.1, so should be greater than 1.6 times 10 minus 4 molar. What is the meaning? The concentration of Cl minus needed to precipitate Pb2 plus 0.1 molar should be greater than 1.6 10 minus 4 molar. 4. Cl minus needed to precipitate Ag plus is 1.6 10 minus 9. Is 1.6 10 minus 9. Cl minus needed to precipitate Pb2 plus is 1.6 is 1.6 10 minus 5 is 1.6. No, we have a square, so radical, this is Cl minus square, implies Cl minus initial should be greater than radical square 1.6 10 minus 4, so the value is 0.026. As a conclusion, to precipitate Ag plus, you need at least 1.8 10 minus 9. 1.8 10 minus 9. To precipitate Pb2 plus, you need at least 0.026. So suppose now As a conclusion, to precipitate Ag plus 0.1 molar implies Cl minus initial in the solution should be greater than 1.8 10 minus 9 molar. To precipitate Pb2 plus in the solution 0.1 molar, you need at least Cl minus initial greater than 0.026 molar. Suppose the Cl minus you add initially in the solution is between 1.8 10 minus 9 and 0.026 implies Ag plus will precipitate and Pb2 plus will not. So as a conclusion, we separate Pb2 plus, Ag plus from Pb2 plus. So now, if you add Cl minus greater than 1.8 10 minus 9, you precipitate Ag plus, and this value of Cl minus you add, suppose is less than 0.026, so you would not precipitate Pb2 plus. You precipitate Ag plus without precipitating Pb2 plus, so you separate Ag plus by filtration. Ag plus will pass completely to the precipitate AgCl. So by filtration, you eliminate AgCl. So in the solution, you will have only Pb2 plus. As a final result, you can say that Ag plus was separated from Pb2 plus. Suppose you add, this is case 1. Suppose now you have case 2. Case 2, suppose Cl minus added is greater than 0.026, implies always the Cl minus in the solution is greater than I will show on a scale, it's easier. I will return to the slides. We have a scale. If you are in this area, no precipitate of PbCl2, AgCl precipitate, so you separate Ag plus from Pb2 plus. If Cl minus in the solution is less than 1.8 10 minus 10, so you don't have a precipitation of PbCl2 nor a precipitation of AgCl, and if Cl minus is greater than the value of 1.6 10 minus 5, so if if IP this is IP on the scale of IP. IP depends on Cl minus initial. So if the Cl minus added in a such way that IP is less than 1.8 10 minus 10, so no precipitation of AgCl, no precipitation of PbCl2. If Cl minus added in the solution give a value of IP greater than 1.6 10 minus 5, so you will have precipitation of Pb2 plus and Ag plus both. And if IP is between this value 1.8 10 minus 10 and 1.6 10 minus 5, so you will have precipitation of AgCl without precipitating PbCl2.